Hi everyone, my name is Blanca. I will be giving my presentation today on the search for dark matter in the form of dark photons at ATLAS. And we'll talk a little bit about the background of ATLAS and dark matter itself, then look at different decays that could be attributed to this dark matter search. And then this idea of fake rates, what they are, how we find them, and how we're going to apply them to this specific analysis. So CERN itself is the European Organization for Nuclear Research. It's the world's largest laboratory located in Geneva, Switzerland. And its goal is to find new physics beyond the current framework. And how it works is that it is 27 kilometers of superconducting magnets that will work to speed up protons to nearly the speed of light. These protons collide and create showers of new particles that we then come in and analyze. And one of the most important discoveries made was the Higgs boson in 2012. And this was very important because it indicates the existence of the Higgs field, which gives particles their mass. So again, we're accelerating particles and having them collide. And these collisions happen at 4 main detectors, one of which is ATLAS. And the beam of particles collide at the center of the detector. And the collision debris fly out in all different directions, and they pass through the different layers of the detector. And each layer is able to record a different variable or characteristic, such as transverse momentum, charge, etc. And from this information, we can reconstruct the collision, almost like a reverse connect the dots, and see the particle decay products and their trajectories. So a little bit about dark matter itself. We know that the universe has been expanding since its birth 15 billion years ago. And it was originally thought that gravity should be slowing down this expansion. However, we found that it's actually accelerating. So this expansion is accelerating, and we're able to see that through things like galaxies being ripped apart. As a result, scientists attributed this and other phenomena to the existence of something beyond visible matter. So things like dark matter. And we know that dark matter is not visible. And what that means is that it doesn't interact with the E and M field. So things like light and charge. And it's not the same thing as antimatter. And they're also not black holes. So possibilities of what dark matter could be have been attributed to things like machos or WIMPs, or specifically this thing called dark photons, which we will look at in this analysis. So dark photons build off the standard model, and we're favoring symmetry. So we're going to extend the gauge sector with this new force carrier, this gamma D or dark photon. And it'll couple very weakly through kinetic mixing with the ordinary photon. And similar to neutrino oscillation, it would kind of bounce back and forth between the regular and the dark photon. But the main theory is that the dark photon could couple to the Higgs. So we're looking at a Higgs decay into the dark photon. Specifically, we're looking at a ZH production. So the production of the Higgs in association with a Z boson. So why are we choosing this? We're choosing this because the Z that decays into 2 leptons is a fairly clean signature. So leptons are fairly easy to detect, easy to trigger in our system. So this gives us a clean signature. And this Higgs should decay fairly evenly in between these 2 photons. So each one of them should have approximately half of the energy of that original Higgs. But if we said that dark matter doesn't interact with our detectors, how are we finding it? And we do this by the absence of energy. So the idea is that you would record all other decay products and see if there's any energy missing from the system, since we know that shouldn't happen due to the conservation of energy. So the final signature that we're looking for is 2 leptons, a photon, and this dark photon energy, which is read as missing transverse energy, or MET. But there's another issue. There is another decay that can mimic the signal that we're looking for. And it's the decay of a WZ pair into two muons, which are leptons, a neutrino, and an electron. So the issue happens when this electron is misidentified as a photon. This happens because the electron and the photon have fairly similar signatures in the electromagnetic calorimeter. So their energy deposits look fairly similar. So there's a chance that they could be misidentified. When this happens, the two decays have a similar signature. So they both have two leptons, they both have a photon, and they both have missing transverse energy. And that happens because of this neutrino is also not read by the detectors. And if we record this misidentified WZ decay as our dark matter signature, we'll end up with more events that are flagged and is read as sort of a false positive. So it's important that we take this into account and determine how often that misidentification occurs and apply that as a background. So how do we determine the rate at which this electron is misidentified as a photon? And there's a formula derived that takes into account exactly that. How many times is the electron correctly identified versus how many times that electron is incorrectly identified? And this is known as a fake rate. And what that is that it basically gives you a probability that your electron is going to be misidentified. So the value of the fake rates on the y-axis is characteristic of that baseline electron. So again, the electron that is being misidentified. So it depends on things like the momentum of that electron and also where it is in the detector determines the probability that it's going to be identified incorrectly. So we have our formula. How do we apply that? So what we're going to do is sort through all events that match this WZ decay signature. And then we look at a specific event, look at this baseline electron, and determine the probability based on the characteristics of the electron. We're going to assign it a fake rate, bin that fake rate, and then move on to the next event. So there are 8 different tables that tell you the different fake rates based on the characteristics, but there's only 2 here. So here we've run through the 2015-16 run to 36 femtobarn data. And that just means it's a small amount of the data. It's not the full set. And so we have a number of events that are potentially misidentified, sorted by their fake rate. So we see there's about more than 400 events with this specific probability of being misidentified. So we've gone through each event, assigned it a fake rate value, and then binned it. These fake rate values can also be sorted by their transverse momentum. So the lower momentum that electron has, the higher probability that it will be misidentified. Again, you can also sort it by pseudo-rapidity or where you are in the detector. So the closer to the beamline you are, the higher this absolute value is, and the higher probability you have of being misidentified. So if we integrate both of these plots, we find that there are about 72 events overall that will be incorrectly reconstructed. So yes, that number is very, very small. So how are we going to use this data? Like, where do we apply this? We're going to apply it as a background. So for example, we have a stacked histogram containing multiple background processes that occur. This fake rate would be applied as a color block on this list and would be stacked on the histogram along with the other background processes. So overall, we are able to take into account the fake rate misidentification of electrons in the search for dark photons. And next steps that we would need to work out are to apply this formula to the full data set. So again, we only used a 36 femtobarn. It's a smaller set of data. And so we need to use it on the whole data set. And another thing is to include systematic uncertainties for a fake rate formula. So all of our values are stat only. they're just like fairly basic. So we need to include things like uncertainty with our values. But for now, that's all I have. Thank you guys so much for listening.